Stars are among the most fascinating things in the universe. They are the givers of warmth, light, and energy, and they are the nuclear engines behind some of the most extreme phenomena in existence. They form from giant clouds of gas, carve out planetary systems, and release heavier elements that allow new stars to form. But the most astonishing aspect of stars is what awaits them when they die. Most stars end their lives in an explosion of unimaginable brightness, a cataclysmic supernova. Yet even that is rarely the end. The remnants of these stellar deaths can become some of the most extreme objects in the cosmos. The most massive stars, many times larger than our Sun, can collapse to form black holes. But death does not always lead to a black hole. Some stars collapse into a much smaller remnant, a ball of matter so dense, so compressed, that its properties are almost beyond comprehension. These graveyard remnants are called neutron stars, and everything about them is mind-bending. To understand a neutron star, you first need to understand a neutron. Everything in the universe, except pure energy, is made of atoms, tiny building blocks made of even smaller particles, protons with positive charge, electrons with negative charge, and neutrons with no charge at all. Protons and neutrons form the nucleus of an atom, while electrons orbit around it. In large stars, at the end of their lives, conditions become so extreme that even these basic components are crushed together. A neutron star forms when a massive star between roughly 10 and 29 times the mass of the Sun reaches the end of its life. Once the star begins fusing iron at its core, fusion no longer produces energy, and the outward pressure that once fought against gravity vanishes. The star collapses inwards incredibly fast, up to a quarter of the speed of light. In the most massive stars, this collapse never stops, resulting in a black hole. But in slightly less massive stars, the collapse halts at an incredibly compressed state, leaving behind a neutron star. An object once hundreds of thousands of kilometers wide shrinks down to something no larger than a city. The density and pressure are so extreme that electrons and protons are crushed together to form long chains of neutron-rich matter. A neutron star essentially becomes one giant atomic nucleus. These stellar corpses possess gravity billions of times stronger than Earth's and magnetic fields so powerful that normal materials cannot even exist as we know them. They are born spinning at incredible speeds, and some rotate tens of thousands of times per minute. Although scientists theorized about neutron stars as early as the 1930s, we didn't confirm their existence until the 1960s. The first big clue was the detection of unusual radio pulses coming from the direction of the Crab Nebula. It became clear that these pulses came from a rapidly spinning neutron star. Later, in 1997, astronomers even captured a visible light image of a neutron star about 400 light-years away, an extraordinary achievement considering these objects are only about 20 kilometers across. A neutron star packs more mass than the Sun into something the size of a small city. One of the largest known neutron stars, PSR J0348+0432, has twice the Sun's mass but is only about 25 kilometers wide. The density is so extreme that a teaspoon of neutron star material would weigh hundreds of millions of tons on Earth. Their gravity bends light around them, creating a gravitational lensing effect. The outer crust of a neutron star is unimaginably hard, with surface temperatures reaching 1,000,000 degrees. The pressure fuses atomic nuclei into strange structures nicknamed nuclear pasta, among the strongest materials in the universe. Beneath the crust, the pressure becomes so intense that normal atomic behavior breaks down, creating matter in a form we cannot recreate on Earth. The magnetic fields, millions to a quadrillion times stronger than Earth's, confine a thin atmosphere only micrometers thick. Many neutron stars appear as pulsars, cosmic lighthouses that sweep beams of radiation across space. If one of these beams aligns with Earth, we detect pulses with astonishing precision. The first pulsar ever found pulsed so regularly that scientists briefly wondered if it was a signal from an alien civilization. But it was simply a neutron star spinning rapidly, firing radio waves like a beacon. Pulsars have been incredibly useful to us. The Voyager spacecraft carries a golden record with a map that uses pulsars as reference points, an attempt to show the location of Earth to any civilization that may find it. The problem is that we now know there may be hundreds of millions of pulsars in the galaxy, and their beams can change direction unpredictably. So the map may be almost impossible for a stranger to decode. Some neutron stars are even more extreme. When a neutron star spins fast enough, its magnetic field becomes monstrous. These ultramagnetized neutron stars are called magnetars. Their magnetic fields are so intense that they can distort atoms themselves and release bursts of X-rays and gamma rays trillions of times stronger than anything the Sun can produce. Fortunately, magnetars are rare and short-lived on cosmic timescales. Neutron stars can also gain mass by pulling matter from nearby stars, especially in binary systems. This can make them spin even faster or even trigger new activity in older, slower stars. When two neutron stars orbit each other, they gradually spiral inward, losing energy through gravitational waves, ripples in space-time itself. In 2017, we detected such waves for the first time from two neutron stars merging in a distant galaxy. Their collision triggered a kilonova explosion, blasting heavy elements like gold, platinum, and uranium into space. These elements help seed new star systems, including, likely, our own solar system. Some neutron stars have planets. These pulsar planets are worlds that formed from supernova debris, were captured from interstellar space, or were once companion stars stripped down to their cores. Conditions on these planets are unimaginably hostile. Radiation would tear apart any molecules needed for life. In one case, a stripped-down white dwarf companion has crystallized into something that may be a gigantic diamond planet. Neutron stars are nearly indestructible, so what happens when they meet something even more powerful, a black hole? In recent years, we have detected gravitational waves that appear to come from a black hole consuming a neutron star. Depending on the size of the black hole, the neutron star might be swallowed whole or ripped apart before falling into the abyss. Some of the torn-off material escapes temporarily, exploding outward before falling back in. The result is dramatic but not as explosive as a neutron star-to-neutron star collision. Neutron stars are among the most extreme creations of the cosmos, tiny furnaces of dense matter, radiation, and magnetic fury. They produce heavy elements that make planets, life, and even our own bodies possible. They destroy, they create, and they illuminate the universe with some of its most powerful forces. They are second only to black holes in mystery and power, and yet unlike black holes, their inner structure can still be glimpsed through the light they emit. They remind us that the universe's most violent events are also responsible for forging the building blocks of life itself.